So with this, we'll move on to the last topic in the, yeah, so that is something that you'll have to, so the way I would do it, right, is that you keep aside some 100 images from your data as validation data, okay. Now once you have learned these eigenvectors, try to compute the reconstruction error for these 100 images. And just vary it, right, do 100, 1000, 10,000, retain as many dimensions as you can and see at what point is the reconstruction error okay for you, right. And this is assuming that you have some notion of what is a reasonable reconstruction error. So we all know that the minimum is 0, right, but if you have 0.5, then maybe for face database it might be okay, right. But if it's a database where you're trying to look at mechanical parts, right, so suppose you're looking at motors and rotors from a machine assembly. Now there you want to be able to distinguish minor defects on this. And a defect could actually just be one single or 2 pixels getting different from the original image, right. So there the reconstruction loss would be needs to be much more robust. You get the point? So it depends on your application. So you'll have to take some validation data, either have a domain expert to tell you what is reasonable or go by the number that you get, right. This is the validation error that I get. So everyone understands the question and perhaps the answer? Okay. So we'll now go to the last module, yeah. If you can. Yes, you can now project any face into this database, right. So that's the eigen basis that you have got. You have got the basis vectors. Now any data you can project onto this basis. Yeah, so now, okay, so if you are trying to learn these eigenvectors by say using 100 images, all of which belong to a particular demographic, say all Caucasian images, right? And now at the runtime you have an Asian image, then you'll obviously have some error, right? But you have large enough data, say if you are constructing this from million images, then it should generalize. That is, I mean, just as for any machine learning algorithm, right? You're training it from small data and you bring out some outlier at test time, it is not going to work, right? But if you have reasonable data, it should generalize. Any other questions? To calculate the eigenvectors, x is m cross 10k, yes. So, okay, so now we will move on to the last topic for the basic portion, and the next class we will do autoencoders, we will be back to deep neural networks. So, singular value decomposition, right. So, this is actually the stuff that I need an important theorem from here at 2 places in the course. So, now before doing this, right, let us get some more perspective on what eigenvectors do and why are they actually important, okay. So, let V1 to Vn be the eigenvectors of A and let lambda 1 be the corresponding eigenvalues. So, we know this A V1 equal to lambda V1 and so on, okay. Now, suppose all the vectors in R, it should be R raised to n. So, if a vector x belonging to Rn can be represented using this basis, okay. Now, what if I am interested in the operation A into x? What is the advantage of representing it using this basis? So, this is what you were saying the other day, right? What is Ax? It's a matrix vector multiplication, right? And it's going to be a heavy computation. Now, if all my vectors in Rn are represented using the eigenvector as the basis, what happens to this matrix operation? It reduces to a, okay, let's see. So, I was interested in Ax, but I know x is this. So, you get this step, and what happens finally? Do you have the matrix anywhere here? So, what happens to the matrix operation? It reduces to a sum of scalar operations, right? If your vectors were represented using the eigenvector as a basis, okay. So, this is one reason why this is important, right? So, you can now get rid of the matrix operations and just do scalar operations, right? Okay. So, now there is a catch here which I am going to ignore just to try. If I bring in the catch, you guys will get confused, so I will ignore. If anyone has that doubt, maybe talk to me after the class. But for now, let's go with the fact that the matrix operation reduces to a scalar operation. Okay. Now, so far what we have done is discussed square matrices, and I have said that they are the villains of linear algebra. But who are the super villains of linear algebra? Rectangular matrices. Everyone says that, but why? Imagine what they do to a vector. Yeah. So, can rectangular matrices have an eigenvector? Yes. Obviously, yes. I mean, any matrix can have an eigenvector. No. Why? Can you write something of this form? You can't, right? Because when the matrix operates on an n-dimensional vector, what does it give you? An m-dimensional vector, right? Hence, they are supervillains, right? Because they take the vector from one space and transform it to a completely different space, right? Completely lost its identity, right? So that's why rectangular matrices are even harder. So now we just saw that for square matrices, these eigenvectors form a very convenient basis where these operations reduce to a scalar operation. But now rectangular matrices don't even have eigenvectors. So then can't we have the same advantage there? Can we have the same advantage there? You can't, right? Because you don't have an eigenvector. But I have to teach you about singular value decomposition, so I better have something. So you get the connection. Okay, there's a problem with square matrices, with rectangular matrices. Okay, so now let's see. So we'll try, the aim is to see if we have something equivalent to the scalar transformation that we had for square matrices. Okay. How many of you have seen this in linear algebra before? So you know whatever I'm going to talk about. Okay, fine. So the result of Ax is a vector belonging to Rm and the original x belongs to Rn. So we do miss out on this advantage that you could have reduced the matrix operation to a scalar operation, and now we'll try to see if we can still get back that advantage. Okay. So notice this is matrix. You can think of it as a function which provides a transformation from Rn to Rm. Okay. So what is the set of inputs to the matrix? It's vectors belonging to Rn, right? That's a set of inputs. Now suppose we had a pair of vectors v1, u1, v2, u2, vk, uk, each belonging to these two different universes. One is Rn, the other is Rm. Okay, and there was this peculiar relation between them that A into Vi is equal to sigma into Ui. Suppose, I'm just being ambitious, let's see whether we can actually have this pair, but suppose we had this pair. Then can you connect this back to the discussion on scalar operations? Okay, okay, so let's just see that in detail. And we'll of course assume that these are orthogonal and form a basis. So the Vi's form a basis in Rn and the Ui's form a basis in Rm. Okay, is that clear? That's all straightforward, right? We have these vectors. Now, every vector belonging to Rn, which was the input space, can be represented using a linear combination of V. Straightforward. And any vector belonging to the output space can be represented of U, right? So that means any x in the input space, I can write it as this linear combination. And now if I do the matrix operation, what happens? You get this A into Vi. What is A into Vi? Sigma Ui. I have still not shown you how to find these sigma Ui's by the way, right? Okay. Once again, the matrix multiplication reduces to a scalar multiplication. Okay. So now let's try to look at a geometric interpretation of this. So what you have is this original space, which is Rn. You are using A as a matrix operation, right, as a function, and you are transforming vectors from N to Rm, right. So yeah, this is the space transfer that I was saying, right. Vectors are being picked up from Rn and being put into Rm, okay. And Rn is a space of all vectors which can act as inputs to this function, and Rm is a space of all vectors which are the outputs of this function Ax, okay. Now we are interested in finding a basis uv such that V is the basis for the inputs. When I say basis, all of you should immediately start thinking of dash vectors, orthonormal vectors, orthogonal or orthonormal, right? Once we have orthogonal, we don't care about the rest. U is the basis for the outputs, such that if the inputs are and outputs are represented using this basis, then all our matrix operations reduce to scalar operations. So we are just trying to find the rectangular analogy for the square phenomenon that we observed. Okay, that's what we are trying to do. Now, can you tell me? I've told you that if such a V and U exists, then you could do this. Can you give me such a U and V? So what do we mean by, so here I said this, right, that the dimension of the row space is actually K and the dimension of the column space is also K. What do I mean by the dimension is, I mean, right here I am telling you this is Rn and this is Rm, and now I am telling you the dimension is K. What do I mean by that? There are only K linearly independent vectors, okay, fine. And this is again something from linear algebra which I expect you to know, is that all possible vectors in Rn, only a subspace belonging to Rk can actually act as input to Ax to produce a non-zero output. So I am talking about null space, column space and things like that, right. So this should be clear. If it's not, it's okay, it's not very important for us right now, right. And hence we have only K dimensions, okay, fine. So let's look at a different way of writing this. So you have this AV1 is equal to sigma 1 U1, AV2 is equal to sigma 2 U2. So I can again do the same trick, that I put all the V's into one matrix where VI's are the columns of this matrix, and I'll put all the U's into another matrix where UI's are the column of this matrix. Is that fine? Everyone okay so far? And then I can write it as this matrix operation. Same thing that we did when we were doing eigenvalue decomposition, right? So we had written it as A into U is equal to U into sigma, right? Because there we had the condition that Ax is equal to lambda x. Now we have AU is equal to sigma V, or rather the other way around, sorry, AV is equal, did I mess up? Did I? No, right? Sorry? Okay, fine, yeah, so AV is equal to sigma into U, okay. So is this fine? No, but when you do the diagonal operation, you will get it as U into sigma, right? The same way as Ax equal to lambda x, but when you write it, it's A into U is equal to, the lambda comes later on, right? So everyone is fine, right? Can I go ahead? Okay. And if you have K orthogonal vectors, so remember I said that this basis consists only of K dimensions, right? Because that's are the set of vectors which can act as input to A. So but I want a basis for the full Rn. So what do I do for the remaining n minus K? You've heard of this Gram-Schmidt orthogonalization, right? So if I give you, if you're trying to construct a basis for n, okay, for Rn rather, and if I give you K orthogonal vectors, you can construct the remaining n minus K using Gram-Schmidt orthogonalization, right? So you can get the full basis, okay, fine. So, okay, let me just see, and this is orthogonal, okay, so you can write, so you see these two forms. Can you relate it to something that we have seen before in the course? This is singular value decomposition. What else did we see before? Eigenvector. So this is exactly the same forms, right? And I've used the same set of tricks to arrive at it, right? So I first put the vectors into a column, as columns into a matrix, then wrote this in the matrix format, and then pre-multiplied, post-multiplied by certain things, and I got these two formats. And remember that V and U both are dash matrices, orthogonal matrices, right? So their inverse is just their transpose, okay. Okay, so far everything is fine. Now I still don't know what U and V are. All this analysis is assuming that I know what U and V are. So now can you tell me how to get these U's and V's? Suppose V, U and sigma exist, okay. Then we can write this, right. So A is U sigma V, so A transpose would be the transpose of that. Now can you work with me? What's the next step? Okay, next. Oh, yeah. Okay, this is U sigma V transpose. So then this would be, I think the next step is, no, next step is also wrong. Is it fine? Okay. Fine, I just had some error with the transposes. Okay. What will happen now? What will disappear from here? U transpose U. That is I, right? Because U transpose is the inverse of U. So you get this. What does this look like? This looks like the eigenvalue decomposition of A transpose A. That means V consists of the eigenvectors of A transpose A. So now can you tell me what U would be? Okay, fine. So this looks like the eigenvalue decomposition of A transpose A. Similarly, we can show that A transpose is equal to U transpose sigma square U. Okay. So then U is the set of eigenvectors of A transpose, right? And now here, what was will the eigenvalue decomposition always exist for a matrix? No. Under what conditions would it exist? First of all, it has to be a square matrix. Okay, right? But now, for a rectangular matrix, would the singular value decomposition always exist? Yes, right? Because it depends on the eigenvalue decomposition of square symmetric matrices. Okay, is that fine? Okay, so for any matrix, you'll always have the eigenvalue, the singular value decomposition. Okay, so this is perhaps, yeah, okay. Now, just one last bit, and let's see if all of you can understand this. So now I can write A in this form. This is nothing but what I already said, right? This is U, this is sigma, this is V transpose. Okay. Now from here, from this step, do you see how I got to this step? This is something that we were struggling with yesterday also, when we were trying to find out summation xi, xi transpose, something similar here. You know the 4 ways of multiplying matrices, right? So this is which way? One of the ways. Okay. Yeah. So does everyone get this? Right? Okay. So a simple thing would be first to just take these sigmas inside, right? Because this is a diagonal matrix, right? These are all zeros. So these are actually, you can write it as sigma 1 u1, sigma 2 u2, and sigma k uk, right? Now this ends up being the product of 2 matrices, right? And you can write it as a sum of columns into rows, right? So what I am writing it as a sum of sigma 1 u1 multiplied by v1. So sigma 1 u1 into v1 transpose is a scalar matrix vector matrix, right? So each of these terms here is a matrix, and you are adding k such matrices. Okay. Now try to relate it to reconstruction error. You are taking a matrix, trying to write it as sum of many matrices. If I trim some terms from this, sum, what would happen? If I have all the terms, then what would happen? I'll get A back exactly. If I drop some terms, what would happen? I'll get an approximation of A. How good would that approximation be? First is depending on the number of dimensions, but is there a natural ordering in these dimensions? If I want to throw away some dimensions, which one would I throw away? Smallest singular values. Sigmas are the singular values. So you see that this is getting multiplied here. Every matrix is getting multiplied by the singular value, corresponding singular value. So if I drop out the terms which have the smallest singular values, then those matrices, the elements would have been very small, so I will not lose much in the approximation, right? So again, the same idea that I am trying to approximate the original matrix by a smaller rank, right? Okay, so now the original matrix had m cross n entries, okay? How much, if I use only k eigenvectors, or k singular vectors or k dimensions to approximate it, how much storage would I need? How many values do I need? So the original matrix was m cross n. How many entries are there here? Each of this is how much? M for ui plus n for Vi, okay, and plus 1 for the sigma. And how many of these are there? K. So if K is very less than your M and N, right, then again you will have some compression. You get this? Again? So all of these ideas are related and I want you to be able to connect them, right, that all of this is towards doing some approximations, reconstructing a matrix from its components and doing this reconstruction in a manner that you end up making minimum error in the reconstruction. Is this idea clear? Even if some part of the math is not clear, is this idea clear? How many of you get this? Okay, so some of you don't, you don't? Yeah, so what is the original dimension of A? M cross N, right? Now I am trying to reconstruct it using a sum of some K terms, okay? So hence this K comes. Now each of these terms, how many elements do I have? I have Ui, which is of dimension M. I have Vi, which is of dimension N, and then I have the sigma I, which is of dimension 1, right? And I have K of these. So this is the total amount of storage that I need. Now I am saying that if K is much less than M and N, which would typically be the case, right, then you are getting a much lower space reconstruction of the original data, right, and you are doing this reconstruction smartly because you are not taking any K dimensions, you are taking the K most important dimensions, and this most important is defined by the singular values. This is defined by the sigma i's. Is that fine? Okay? Okay. And actually there is a formal theorem which says that sigma 1 U1 V1 transpose is the best rank 1 approximation of the matrix. Is this a rank 1 matrix? Is sigma 1 U1, I hope you guys have done the assignment. Sigma 1 U1 V1 transpose is a rank 1 matrix, and if I take this idea further, this summation is the best rank 2 approximation, and if I keep going, this summation is the best rank K approximation. So what it says is that if you are trying to reconstruct the original matrix, right, from these components, and if you go by the eigen or the singular values and you pick the ones corresponding to top K singular values, then that's the best possible reconstruction that you could have done. Okay. Now, how do you formally define reconstruction? How would you make it as an optimization problem? What are you trying to minimize? The actual matrix has some values, which is the matrix A, okay. B is the reconstructed matrix using only K dimensions. How many of you understand what is this product saying? What is this? First K columns of U, okay. These are the K singular values and these are the first K rows of. So, okay, I was just talking about this. This is the first K columns of U. These are the K singular values put across the diagonal, and this is the first K rows of V transpose, okay. And this is exactly the product which I showed you here. Is that fine? Okay. So there is a theorem, this is called the SVD theorem, which says that if you want to reconstruct A, then this is the best rank K approximation that you can get. Now, if I want to pose it as an optimization problem, what will I say? What would I have minimized actually? This is the reconstruction, right? So let's call it A hat actually. And what does this mean? This is the dash norm, Frobenius norm. What does the Frobenius norm give you? Square difference between the elements, right? Roughly speaking, okay. So it will tell you what's the square difference between the ijth element of A and the ijth element of B. So whenever we have this situation, if you are trying to, if this is our objective function, that we are trying to reconstruct A or try to transform something and get a predicted A or a reconstructed A, then the best possible reconstruction would be given by this solution. So this optimization problem has a solution that you just use the eigenvectors of XX transpose and AA transpose and A transpose A, right? Is that clear? Okay. So this is the theorem that we'll be using when we are talking about autoencoders, and we'll try to connect autoencoders to PCM. Okay. So just revise this. This is the prerequisite for next class. Whatever we have done in the last 3 sort of extra lectures, you have to revise it before you come for class tomorrow, right? Okay. And yeah, this is sigma is just some terminology. Sigma is actually the square root of lambda I, that was obvious. And U is called the left singular matrix of A, and V is called the right singular matrix of A.